Hello, in the last couple of classes we have looked at the semiconductor and we have also looked at the p-n junction. In these classes we have been looking at a series of topics associated with the idea of capturing solar energy in the form of directly in the form of electricity and essentially using a photovoltaic process to enable that. So, it is in that context that we looked at the semiconductor as well as the p-n junction. When we looked at the semiconductor as an independent entity, we looked at its band diagrams, we looked at the origin of those band diagrams, we tried to at least briefly look at how the internal structure of the material impacts the band diagram and the behavior of the electron with respect to that internal structure creates that band diagram. We also looked at those flat band diagrams, we looked at the E versus K curve and how those interactions between E versus K curve and the periodic structure of the element creates the band diagram for you. Then in the next class that we looked at the p-n junction, where we are looking not just at an individual semiconductor, but at the idea that you can take two different semiconductors, one which is p doped and one which is n doped, and then bring them together. At least conceptually that is the way we would look at it. And then we try to understand what are some characteristics that happen that are there for such a junction and possibly what could happen if you bring such a junction together, what would be its operational characteristics, so to speak. We also looked at how the energy of the p side will look like with respect to the n side, and that the idea of this Fermi energy being constant, and then that there are some band bending features that appear. So, these are all the things that we looked at in the last couple of classes. It was a little bit intensive from the science side of it. We will get back to that and take that forward from our next class. In this class I wanted to do something which is a little bit more technology oriented to get a better sense of how this technology comes together, because we now know what the semiconductor is. We understand that there is something called a p-n junction. We understand that we want it to be we want the junction to be good even at an atomic level. For example, I indicated to you that it does not help if you take separately a p material and an n material and then you press them together. The contact between those two surfaces is so bad, even though visually we do not realize it. It seems like two polished surfaces have been pressed against each other. Visually we do not realize it. The contact between those two surfaces is so bad that it would perform extremely poorly as a p-n junction. So, we do while we understand the science of it, we also need to acknowledge the practical aspects of it and actually create this junction in a way that that will work as predicted based on the characteristics we are expecting. So, in this class we will actually look at growing the single crystal and making the p-n junction and some associated aspects, although the title is on the single crystal. We will also look at amorphous silicon, and we will look at various characteristics associated with it. So, there is a little bit of technology orientation for this class. We will get back to the science of it in our upcoming classes. So, our learning objectives for this class are to become familiar with the techniques used to make single crystal as well as amorphous silicon. So, that is our learning objective, main objective. So, there are some specific techniques. It is a good idea to get a sense of what those techniques are. So, you see a chip, you see it, and you go see a solar panel, you see a chip there. You can also look at semiconductor chips which may be there in various places in electronic devices that we use. But where does that come from and what are some challenges in putting that together? So, we will look at that. So, techniques used to make those single crystals as well as an amorphous version of it. And having understood that, we will also briefly look at starting from there how you would make a p-n junction. So, these are two things that we will look at as we go through the contents of this class. Okay, so, to do this more specifically, we will look at two processes. One is called the Czochralski process and the other is called a float zone process. So, these are two processes that are used to create that single crystal. They have some details associated with them, at least briefly we will consider that, so that you become familiar with when you see a single crystal, what is the effort that has gone in towards making it. We will also look at something called zone refining. It's an idea that is used to purify some material, and purity is a very critical thing in semiconductor industry, and we will see some parameters associated with purity, what kind of level of purity we are talking about, and therefore how challenging it is. and therefore, you need some special techniques to do it, and zone refining is one of them. So, we will talk about it. We will also look at how wafers are cut, because finally initially when we go through this contents, we will see that what is first created is a pretty big object, solid object. It's not anything like what you see in your computer, and therefore that, or on the solar panel, and therefore that has to be cut into very fine slices before it can be used anywhere. So, that is something we will look at. We look at amorphous silicon, how that comes about, and finally we will look at how PN junctions are manufactured. So, this is what we will do. So, as we go over this, I think what you will find as a common thread that goes through this set of topics that we are going to look at in this class is the fact that there is something associated with crystal structure. Okay. So, particularly we are talking of terms such as single crystal. We can also talk in terms of a polycrystal, and we can talk of an amorphous material. Okay. So, amorphous material. So, these are three different kinds of material that we can consider, and that is the thread that runs through. So, the same material, essentially the same material. So, in this case, for example, we are talking of silicon. Silicon can be made available to us in all these possibilities, as a single crystal, as a polycrystal, and as a amorphous material. So, we'll start off first by understanding what is the difference between these, and then from there we will move towards each of these techniques. So, if you see here, what you see on your left top corner is what we would refer to as a single crystal. Right. So, what does that mean? A single crystal basically means that if you start from one end of that material, you will see crystal in order. So, you are going to see, start from this end and you move in some direction. Let us say you move some distance A and you arrive at one plane, a crystallographic plane. Then if you continue another A, you will again arrive at the plane, one more A you will arrive at the plane, and so on. And this process will continue all the way till the end of the crystal. So, you can do this and you arrive at the end, right. So, all the way to the end, from one one starting point in the crystal to the end of the crystal, the atomic planes will be in perfect order. Okay. So, when I say from one end to the other, I am talking of from one end to the other of an object, okay, an object that you can hold in your hand. So, some big object that is sitting in your hand, which you can hold and lift up with your hand. From one end of the object to the other end of the object, the atoms are in perfect alignment. Okay. So, they are perfectly aligned from one end to the other. So, therefore, if you see one orientation of atoms on one end, you will see exactly the same orientation at the other end. So, something like that is referred to as a single crystal, and that is not easy to manufacture. It takes a lot of effort to get us that kind of a sample, where you can have this big block of materials sitting in your hands, where there is perfect atomic order from this end to the other end. What we are more likely to see are more along the lines of B and C. Okay. So, both of these are polycrystalline materials. So, this is also polycrystalline. Okay. So, both of these are polycrystalline. So, now the what you see here, for example, are boundaries. So, this is a boundary, this is also a boundary here. You can see some specific boundaries here, I am just tracing them out for you. So, it is easy to see. So, these are boundaries. So, now what it means is, if you start off from one end of the crystal. So, first of all, even this end of the crystal itself, if you go from the bottom of the crystal to the top of the crystal, you do not see the same order. Okay. So, at the top of the crystal you see these planes vertically down. Let us assume you are looking at the same plane, you see those planes vertically down at the top of the crystal, but those planes happen to be at an incline at this end of the crystal, bottom end of the crystal, which was not true on the in the example that we saw here, right. So, as you start off itself, when you go from the bottom of that sample to the top of the sample on your left hand side of the sample, let us say, the order is not maintained. And further, as you move into the crystal, as you move away from that end, as you approach this end, you will find at various locations such as this, the orientation will change. So, in this example, for example, it is just changing in one place. So, it changes here as you go from the left to the right, following the path on the bottom of your sample. but that can vary from sample to sample. You may have had 3 divisions in the middle, you might have had 100 divisions in the middle and so on. So, this idea that you have crystalline order only up to a certain location, so for example this location, and then after that there is a breakdown of order, at least at that boundary, at this boundary area there is some breakdown of order. So, there is some breakdown of order there, and then again order starts in this location. So, you see some crystalline order in that location, again order breaks down in this region here, and then once again you have crystalline order. So, this idea that you have pieces of crystalline order with boundaries in between them is then referred to as a polycrystalline situation. Okay. So, this sample is polycrystalline in nature, it has many crystals, that is why polycrystals, which are now distributed across the sample. So, what is the difference between these two? The main difference is the crystal size. Okay. So, this is a small crystal size, and this is large crystal size. So, that is the difference between these two samples, both are polycrystalline. So, in both of them as you go from one end to the other, you see so many boundaries here. So, for example, this is a boundary that is, so this region is crystal, the a neighboring region has a crystal oriented differently and so on. I mean it is just a pattern that I have put there, but it could be in any shape, it does not even have to be so uniform in size. Okay. So, this happens to be a uniform grain size crystal size sample, but this is not so B is not so, whereas C happens to be a very uniformly sized crystal sized sample. So that is just a variation. So, you can have small crystal size, you can have large crystal size, etc., and you can notice that the 4 samples that are on screen at least for visual examination are essentially the same size. So, you can think of physically itself samples of the size that you are holding in your hand which are having all these characteristics. The final sample that we have here is what I have marked as D, which is a sample which is having complete disorder as you start from one end of the sample and you approach the other end of the sample. So, as you go from one end of the sample to the other end of the sample, there is no sustained crystalline order to any degree that you can seriously measure. So, it is basically an amorphous sample. So, it is an amorphous sample, there is no crystalline order. So, you start from an atom, you head off in some direction, you may find another atom. If you continue in the same direction, the same distance, there is a chance that you will not find the next atom. You have to go a little bit to your right or a little bit to the left to find the third atom. Then from there again you move forward in that same direction, again you may have to go a little to the right or a little to the left to get to the fourth atom and so on. So, it is just in a disordered way those atoms are sitting, and so that is an amorphous sample. So, this is the layout that we have of structure that you can have in a material, and silicon for example is available to us in all these possibilities. You can get a single crystal silicon, you can just you can buy commercially, you can buy or you can make in your lab single crystal silicon, polycrystalline silicon with large crystal size, polycrystalline silicon with small crystal size, and amorphous silicon. All of these are possible. And as you may expect, it turns out that because of the existence of these boundaries, so essentially we are talking of something that is starting from high degree of order. This is high, single crystal is a highly ordered sample. You are increasing the level of disorder as you go to a large crystal size sample, even more disorder when you come to a small crystal size sample, and then finally a very significantly disordered sample, which is your amorphous sample. Okay. So, it turns out that as you increase the level of disorder in the sample, the properties of the sample change. Okay. So, there is some variation in property, sometimes that property changes in some kind of a predictable way, and then it may be that you have multiple trends. You have a trend for some range of crystal sizes, then you have another trend for another range of crystal sizes and so on. And it is in this context that you in fact you even have this field of nanomaterials. So, when you go to these polycrystalline samples and you start reducing the crystal size more and more and more, the way the property changes actually becomes very interesting. So, whereas it may have had a certain trend up to a point as you keep decreasing the crystal size, when you go to very fine crystal size, suddenly the trend becomes inverted or it becomes something totally different, and therefore, the same material is now suddenly available with you with some properties that you never anticipated that material will have. And that is the whole field of nanotechnology, regardless of which nanomaterial you are talking about. The idea that when you go into that nano scale with extremely small crystal sizes, the material behaves dramatically different from the exact same material in a large crystal size sample. Okay. So, that is anyway something that we can keep in mind. So, anyway, so we can get silicon in all these possibilities, and as we look through the techniques in this class, This is essentially what we are going to do. We are mostly trying to look at techniques that get us the single crystal, and then in the end we will also look at techniques that get us this amorphous sample. Okay. So, but in general if you look at say solar cells, you can get single crystalline solar cells, you can get polycrystalline solar cells, and you can get amorphous solar cells. Cost wise that is the order. I mean the single crystal is most expensive, the polycrystal is less expensive, amorphous is relatively the cheapest of those cells. Okay, so if you go all the way to the beginning and start where you are going to get the silicon. Silicon is well abundantly available, it is sand, it is there as part of sand. So silica is there in our sand. So what normally happens in the silicon industry is that we first start with sand, we find some good quality sand which is relatively pure, which does not have too many impurities in it and so on, and we take that sand and we create something called metallurgical grade silicon. Okay, so metallurgical grade silicon is what we try to generate, and this is basically starting from sand which is SiO2, and then you can essentially reduce it and you get silicon. So, and for that primarily you take SiO2, you add coke and you add heat, and then you continue that reaction process. It has some steps associated with it. I am not going into the chemistry in a great deal, but this is the basic idea. You start from silica and then you get silicon. SiO2 becomes Si when you go from quartzite, which is a relatively pure version of sand, to silicon, which is the metallurgical grade silicon. So, this is sort of bulk processing of silicon, and this is relatively inexpensive. You can get significant quantities of metallurgical grade silicon. This silicon is 98% pure. Okay, so 98% pure. Many times when we think of purity, 98% seems like a good number. I mean, you say okay, it is pretty pure, it is pretty good, pretty clean material, but if you actually look at what is required with respect to the electronic industry, 98% is like which means 2% impurities. 2% impurities is an extremely poor quality sample. It is an extremely poor quality sample to the point that you really cannot do anything meaningful with it. It will not give you the properties that you want. It will give you really bad properties. You cannot really run any significant test with it, you cannot really do something, you cannot really create the kind of devices that you would like with a material that is only 98% pure. So, from metallurgical grade silicon we need to create something that is referred to as electronic grade silicon, EGS. It is also referred to as semiconductor grade silicon. Okay, so it is electronic grade silicon or semiconductor grade silicon. You can see here the difference, what was 2% impurity now suddenly drops to ppm, parts per million of carbon and oxygen in it, and parts per billion of any other metallic material present in it. So, this is a remarkable shift from going from several orders of magnitude you are changing in purity when you go from something that is 98% pure to something that is having parts per million of impurities, parts per billion of impurities and so on. So, to do that, in fact what they do is actually a process where you take silicon solid. So, you have to start with silicon solid and you have to arrive back at silicon solid, right. So, you are going to start with silicon solid, you are going to do some processing. So, it may in the middle it may become something else, and then in the end you again get back the silicon solid, except that now it is a purer silicon solid. So, that is essentially the idea in this step here. So, if you consider this as step 1, this is essentially step 2. So, step 2 is you take silicon solid, you react it with HCl, and you will essentially get this trichlorosilane gas, trichlorosilane. So, that is it is in gas phase, and then once it is in the gas phase we can purify the gas. So, it may have other constituents in the gas, we do some separation, some kind of fractional distillation, etc., etc., and then you can separate out the trichlorosilane such that you now have trichlorosilane in a purer form, you do not have anything else along with it. Okay, so that way we separate out this silicon fraction, and then you again reduce it back to silicon, you reduce it back to silicon. So, in many ways this reaction is the same, you simply go in the forward direction initially to create this trichlorosilane, and then go in the reverse direction to get back your silicon. So, you set the conditions such that it will go in the forward direction, get this trichlorosilane, and then go in the reverse direction, get back your silicon, except that in the middle there is a purification step. The trichlorosilane is separated out from any other constituent that is there, and so you have a purer version of this trichlorosilane that is then reduced and you get back your silicon. So, when you do this process you get this electronic grade silicon. Okay. So, that is how you arrive at this electronic grade silicon. Most likely that sample is going to be polycrystalline in nature. Okay. So, most likely you are having a polycrystalline electronic grade silicon, which is so a pretty significantly pure silicon sample, typically polycrystalline in nature, which is going to be available to you, which on which you have to do further processing to generate whatever sample you are interested in working with. Okay. So, this is the base background situation from where we start, and then we try to create the samples that we are interested in. So, from here we will now move to the Czochralski process. So, in the Czochralski process what we do is we are trying to now the next two processes we are looking at, we are trying to create a single crystal of this sample. We have electronic grade silicon available to us, from there we would like to create a single crystal of silicon. So, there are a few things that are done there. Essentially what is the basic idea is you have to melt this material, and then when it recrystallizes you have to set the conditions right that it recrystallizes as a single crystal. That is the basic idea. Okay. So, you take something that may be polycrystalline, in which case the atoms are the order is being broken repeatedly at several locations, which are those grain boundaries, and then you melt it so that you now have atoms in a molten state, and then when it recrystallizes you do not allow them to break order, you try to encourage them to stay ordered. So, that is the basic working principle here. So, what we do here is we have a crucible, a quartz crucible in which we have molten silicon. So, you have molten silicon. So, this melting point is about 14 degrees C. So, molten silicon is there. This is electronic grade silicon or semiconductor grade silicon. This is what is being used here. And the crucible itself is actually of a higher melting point, 1670 degrees C or higher, based on the exact phase that is there, but that is the melting point that is present there. And you have to heat it. So, you have to first heat it. So, you have heating coils here. These heating coils are essentially using this induction process, sort of like the induction stove that we that seems to be prevalent these days. It is an induction process. So, you have an alternating current with radio frequency, RF frequency current that is flowing, and that causes induction, and because of the induction there is heating, and because of heating the silicon melts. Okay. So, that is how the melting occurs, and we are trying to maintain about 1425 degrees C, which is just above just a few degrees above the melting point of silicon. So, we melt it, but we do not go to a very high superheat, we just stay just a little bit above the melting point. The reason being, from this melt we want to crystallize something. So, what is crystallizing has to naturally be a little cooler, only then it will crystallize. So, we have to maintain the liquid at a slightly higher temperature, the solid at a slightly lower temperature compared to the melting point, and then in that process you can keep the solids separating. So, this is the basic idea. So, on both sides you have these heating elements, and we have some inert atmosphere, because we have already taken some effort to prevent impurities from coming into the system. So, we want to make sure that we do not reintroduce impurities. So, you keep an inert atmosphere so that impurities do not come in. However, if you want to do doping, so this is a good time to do it. So, you can add either boron if you want to create a p-type semiconductor, or phosphorus if you want to create an n-type semiconductor. One of those two can already be added into this melt, so that the single crystal that forms will automatically already have this boron or phosphorus present in it. So, the doping can be taken care of in that sense. So, we have molten silicon, and then what we do is we first introduce something called a seed crystal. Okay. So, in the next slide I will show you that in a step by step basis. In this I am showing you the overall picture. So, we introduce something called a seed crystal, which is right now up here. So, originally that seed crystal would have just come in contact with this molten liquid. Okay. So, once it comes in contact with the molten liquid and there is cooling occurring very close to this, then what happens is the liquid begins to solidify. The atoms in the liquid begin to attempt to solidify. They will try to solidify on this seed crystal. So, the seed crystal is a small single crystal which you can easily cut out of a polycrystalline sample if you wish, where you know the orientation. So, you know the orientation, you keep that orientation. Some crystal surface is there at the front of that crystal, and that comes in contact with that molten liquid. When you do that, the atoms which are below actually in the liquid state find it energetically more favorable to line up with the atoms that are in the solid instead of randomly lining up. So, they line up, they are given a chance, they will line up with those solids, because that is the lowest energy state for them. If they did not line up with the atoms in the solid, that is a little higher energy state. So, if you give them a chance, they will line up. So, and you are at the melting point, so you are in a position to give them a chance, and to actually increase that chance you actually rotate that very slowly you rotate the seed crystal, you also rotate the crucible. By rotating it, you are giving the atom some level of movement without too much movement, some level of movement, so that they can keep reorienting and then getting into the lowest energy state possible. They have enough thermal energy, you give them some ability to reorient, they reorient and you get this lowest energy state lining up with the atoms in the seed crystal. And then you gradually pull that seed crystal out, very slowly you pull the seed crystal out. So, you are pulling it out at 25 millimeters an hour. Okay. So, just 2.5 centimeters every hour. Every hour you pull it out by 2.5 centimeters, slowly, gradually it is getting pulled out, averaging 25 mm per hour. Okay. So, when you do that, this single crystal begins to grow. So, as you keep pulling it out, more and more liquid keeps solidifying, and in all the solidifying liquid is forming a single crystal in line with the seed crystal, and then it continues to grow, and then eventually you have a large single crystal, and you have essentially consumed all of the molten silicon that is present. We of course just have some holder here which is being referred to as a chuck, and the chuck holds that seed crystal, and it can be rotated. So, that is the basic idea that we use in this Czochralski process, and you get this single crystal that grows. Generally, given the nature of the dynamics of this whole process, the induction heating that is happening, the kind of conditions under which we are operating, generally the kind of diameter they are able to succeed to get is about 200 to 300 millimeters diameter. These days they are finding ways to make even larger single crystals, larger diameter single crystals, but this is the kind of diameter you are looking at. I will also tell you that in both these processes, the Czochralski process as well as the next process that I am going to talk about, the because there is liquid which is trying to solidify onto a solid, there is always some surface tension related behavior. That is the reason why you get the circular shape, circular cross section. Okay. Otherwise you could even get a square cross section or some other cross section, but because it is a liquid which is in a position to shape itself based on its surface tension, you get that circular cross section, because that gives it the least perimeter, and if it were 3 dimensional, it will take the spherical shape, but here your position of interaction is a 2 dimensional surface, the bottom of the seed crystal and the top of the liquid. So, you only have a 2 dimensional surface there, they are in contact at a 2 dimensional location. So, there instead of a sphere it takes a circular shape, and so these single crystals that grow are typically circular in cross section. And so, what you eventually get, what you are seeing here is actually a cylinder. It is a cylinder, cylindrically shaped single crystal. In fact, that is the reason if you look at solar panels where they have used slices of the single crystal, you will see circular cross section there. You do not see some random shape, you see circular cross section. So, anyway, so that is the idea of the Czochralski process. It is Czochralski is the person credited with it. Apparently, he discovered it by accident, and he found that when he was working with some melt, he could pull out a single crystal by contacting it and then pulling something out which was cooling very well. So, that is the basic idea. So, this is one way in which you can generate the single crystal. The same thing in a stepwise sequence I am just showing you here, the same Czochralski process, just to make it better, make a better image in your mind about what is happening. So, you can say you are starting off with this situation here, you are melting polycrystalline silicon and adding dopants if you want to add dopants. So, at that point you simply have a melt, you have a melt that is here, and you can build up the melt to how much ever degree that you want, and it is a high purity melt. Okay, it is a semiconductor grade silicon that you have used, so it is a high purity melt. So, in the next step of the schematic we introduce the seed crystal. So, that is the seed crystal that is sitting here, it is a small single crystal as I said, and it comes in contact with this liquid at that one location there, and then you start slowly, you start pulling this out, you start pulling this out. So, you can see here this is the growing single crystal that has started appearing. Okay. So, as you slowly pull this out over a period of time, what is happening is this two things are happening, your single crystal is growing, and of course, the liquid is getting consumed. So, the liquid level is continuing to drop, the single crystal is continuing to grow. So, those two things are happening. So, in the end you will have a relatively tall single crystal up to here, and then a very small amount of remaining liquid. So, this is the basic process, and so that we would call as your completed single crystal process. So, this is what we have, and further processing is done with this single crystal. Okay. So, that is the Czochralski process as an overview, and you can look up more details of it. It is a pretty extensively used process for single crystal manufacture. The other process we have is called a float zone process. Okay, so another process here called the float zone process. So, it has some advantages and disadvantages over the Czochralski process. So, the first thing is in the float zone process we do not melt the entire silicon. Okay, so we do not start off with a melt, we do not start off with a molten a container full of molten silicon, that is not our starting point. Instead our starting point is actually a rod. Okay, we pick up a polycrystalline rod. So, for example, the top part of this sample that you see here is that polycrystalline rod. Originally the entire sample would have been polycrystalline from top to bottom. So, I have something here called the upper chuck and then there is the lower chuck, these are the two things that are holding that sample together. Originally from the upper chuck to the lower chuck entire thing would have been a polycrystalline silicon rod. Okay. So, that is what we would have had. At the bottom we have a small seed crystal, at the bottom we have a small seed crystal. Now, the interesting thing that we do is we have heating coils, same process we are using some RF based heating coils, but these heating coils are moving. So, they are moving. Okay. So, we have heating coils that are moving upwards and therefore, their sphere of influence is a very small region. So, that is the region, that is the sphere of influence, that is where the sample is actually hot. So, the sample may be cold on top, may be cold at the bottom, but there is a region in the middle which is hot. So, you have a small molten zone, that is what you see here in this region, that is your molten zone. So, the silicon melts there alone locally. Okay. So, there alone it melts and it has some shape mainly because of surface tension effects, it has some shape, it is trying to minimize its surface energy. So, you get that kind of a shape and it melts. So, on top you have polycrystalline sample, in the middle you have this melt, in the bottom you have a solid. So, given that you have a seed crystal and you have given that melt some opportunity to align itself with respect to that seed crystal and that is the direction in which it is cooling, it begins to form a single crystal at the bottom. So, this becomes a single crystal. Okay, so that becomes a single crystal. The bottom becomes a single crystal because seed is there and plus you are moving away from that direction. So, you are continuing to melt towards the polycrystalline side, you are continuing to solidify towards the single crystalline side, and because you do this steadily the sample becomes single crystal from bottom to top. Okay. So, the big advantage here is that you are not having to melt the entire sample. Okay, and here also you use argon because you want you do not want to introduce further impurities into the process. So, you do keep a inert atmosphere, but the main disadvantage perhaps is that because you have this this small region that is that has to hold a stable physical state in without collapsing and is limited by surface tension forces and so on. So, there is some limitation to the size or the diameter of this rod that you can use. So, generally it is found that about 150 millimeters is the sort of the largest diameter sample that you can create using this process called the float zone process, where you just have this small region of melt that is moving up, and that is primarily due to surface tension. But the nice thing is you get very high purity, you get much higher purity relative to the Czochralski process. In the Czochralski process you do get some impurities from that the quartz crucible. The quartz crucible is adding because it has SiO2, it is actually adding some amount of tiny amounts of oxygen into the process. It also gets affected a bit by the thermal process that is occurring there, and so therefore some the level of purity that you get here is a little bit less than the level of purity that you get with the float zone process, and therefore from the purity perspective this is better, but size wise you get a little larger size if you work with the Czochralski process. So, these are two major processes that are used to create your single crystal silicon, and the focus is to both be single crystalline and also to have high purity. So, in this context we will also look at the idea of zone refining, which is primarily focused at the purity aspect of it. You already got a single crystal, what can you do to purify it? Okay. So, in some ways it is also related to the float zone process because the general idea is the same. You will have this kind of a single crystal now from bottom to top, but you can do this moving melting in this case as you move this heating coil, the molten region is moving from the bottom to the top, right. So, the whole sample is not molten, only one small region is molten, and that molten region is moving from one end of the sample to the other end of the sample. So, that is an idea you keep in mind. We go ahead and look at this situation here. What you see on your screen is a phase diagram, a section of a phase diagram of some hypothetical material. We will assume, let us say, it is a section of a phase diagram, let us say for silicon, but the point being, on your y axis you have temperature. So, that is what you have here. On the x axis you have composition in percentage B. So, percentage B is any impurity. In this case it is some impurity that is there in silicon which you do not want in silicon. So, you want to remove it. So, in fact you want this percentage, you want to be as close to this end of the your final sample to have a composition as close to this end of the x axis as possible, right. Supposing you start with a sample that has this composition. Okay, so, you start with a sample that has this composition and you start cooling it. So, we call this the liquid S. This is the liquid state, this is solid state, and this is solid plus liquid. Okay, and this is called the solidus. This line is called the solidus. Okay, so, what this means is, if you take this composition and you start cooling down, if you stop here, if you are at this temperature, let us say you are at this temperature, at that temperature the sample will be entirely in liquid state. Okay. The same composition, if it were at this temperature corresponding to this region on your y axis, then the sample will have partly solid, partly liquid, and we can use the lever rule to find out how much of it is liquid, how much of it is solid. If you were at this temperature, this sample would be entirely in the solid state. Okay, so, this is how the phase diagram works. Now, what is of interest is the transition that happens when you are between here and here, where you start off being completely liquid and you arrive to a state where you are completely solid. Okay, so, when you do that, the interesting thing about this phase diagram is it tells you how what is the composition of the solid that is separating out at any given instant, okay, at any given circumstances. Even though you start off with a liquid that has this uniform composition, okay, so it is uniform composition, what happens is, as a virtue of this phase diagram, the first solid that comes out does not have this uniform composition, in fact it has this composition down here. Okay, so, that is the composition that the first solid that comes out of this liquid will have. Progressively, as you keep decreasing the temperature, the next, I mean, if you go down somewhat further in temperature, you will have solid that is coming out with this composition, etc. So, the composition of the solid that comes out will slide down this line. Okay, the composition of the liquid will slide down this line. Okay, so, in the end you will have a solid which is a single crystal in this case. But the point is, if you have done this, the solid this single crystal, let us say you started at the bottom and you finished off this process at the top of that single crystal, the bottom will have this composition, the top will have this composition. Okay. So, therefore, you will have a situation where basically the composition has been changing continuously through this sample, right. So, therefore, the end of the sample which solidified first is actually a much purer sample than the end of the sample that solidified last. So, therefore, you can do this process and you can remove the last part of the sample which was impure, and you will have now a sample which may be slightly smaller in size, but has higher purity than the sample you started with. You can continue this process repeatedly, and each time you do this you will keep getting one end of the sample that keeps getting purer and purer and purer. So, this is a process they use to make this overall sample as pure as possible, and that is how you get this high purity sample. So, in fact, if you do this in an equilibrium state, then you will actually move across the composition of the entire solid will move up along this line, so that the final solid has this composition, but normally we do it in a non-equilibrium sense. So, you will actually have a range of compositions in the solid. So, you will such that the overall average composition is this. Okay. So, the average composition you cannot move away because that is a composition of the solid, but it will not necessarily move down this solidus because you will be doing it in a non-equilibrium sense, right. So, in fact, you will have a range of compositions, and you will have not exactly finishing off with this exact composition that you see on you will not follow this line directly, you will be a little bit away from the line because you are doing it in a non-equilibrium sense. So, that is the practical aspect of it, but this is the concept behind it, and you can keep getting a solid that is purer and purer and purer. So, that is zone refining, that is used for refining single crystals. So, now that you have a solid single crystal available to you in the form of a tubular structure, what is the next step that is done? The next step that is done is basically slicing of silicon ingot to get wafers. So, that is what we keep hearing, silicon wafer is a term that we keep hearing. This is what is happening at that point. So, they have taken this cylinder that we got through the single crystal process, either Czochralski process or float zone process, and then we purified it. All that we did, we are now satisfied that the quality of that single crystal is what we want it to be, the composition is right, the orientation is right, all that we figure out. Once we have figured all that out, we do this slicing. So, normally what they use is they use a diamond cutter, diamond cutting wheel, and they use the inner edge of it, that is why it is called this inner diameter slicing, and then you slice the silicon wafers one by one, you get a slice, and typically those silicon wafers are about 0.2 to 0.75 mm thick. There are some limitations because if you get thinner than this, you may actually you will have some problem in stably making it. So, you tend to get in this dimension 0.2 to 0.75 mm thick, but this kind of a cutting process will get you one wafer at a time. They also have some other processes which is based on some wire saw. So, wire saw that you see here can be used where you basically have a thin wire with an abrasive slurry, and then you can have several of these thin wires or the same wire wound in different directions, etc., so that you can cut the sample simultaneously at several locations, so that at an instant you get a huge number of wafers. Okay. So, simultaneously the wire is cutting the same cylinder at several locations, and therefore you end up getting several slices. So, that is another way in which you can get several wafers at the same time. So, this is an important step. Once this is done, there is still some cleaning that is required of the surface of that sample, and also to make it as flat as you would like it to be. So, there is still some processing steps involved, but this is the after you have made the single crystal, the next major step is to make this wafer, and this is the general idea, that you just cut it slice by slice by slice and you get this these wafers. So, that is the next major step. So, having done this, what is also done in the semiconductor industry, so that it becomes easy, because once you have all these wafers, it can get very confusing. You have doped them in P doping, you have done N doping, and usually based on the crystal faces that are available, you can either have 100 planes on the as being the planes that are the parallel to the top surface. So, the entire cylinder consists of 100 planes going from one end to the other, or you can have 111 planes going from one end to the other. So, these are the two crystallographic planes oriented with respect to the face of the cylinder of the cylindrical sample that are most commonly present in these silicon single crystals. That does not have to be true for other systems. In this system, these are the two that are of interest, that typically these samples are made in this form. So, just to make it easier for people to just look at a sample and say, okay, this is N type or P type, and this is 111 or 100 plane on the surface, they usually use notches. So, this is a notch that you see here. So, you can see what was a circular cross section, a small bit of it has been cut off. So, you can have this initial notch that is present here. If you have only that notch, it means it is a P type sample which has 111 orientation on the surface. If you have this notch as well as another notch perpendicular to it, it is still a P type sample, but it has a 100 orientation associated with it. Instead of this second notch being at 90 degrees to the first notch, if you had it on top, then that is an N type sample also with 100 orientation. And finally, you can have N with a 111 orientation, where you have this initial notch as well as this notch on the side at the edge at an angle to it. So, they do these notches to help you quickly identify at a glance what are you dealing with, N type or P type, 100 or 111, and that is useful for further processing or further any further activity you want to do with the wafer. This is a very important piece of information, and you cannot keep on going back to the X-ray diffractometer to find out what sample you have, what orientation is it, what is the composition, is it P type or N type, using some analysis technique. You know initially what it is, so you just mark it in such a way that you can see it permanently. These days they have come up with some, for larger wafers, they have come up with a slightly different kind of notch process, or at least there is some modification on it. So, but this is still there in many of the samples that you are going to see. So, this is another important step. So, you made the single crystal, you did the slicing, you introduce these notches. So, this is what we have done, and then that can be used. So, we will talk briefly about how it can be used in the next slide, but before that we will also talk about amorphous silicon, because that is another this so far we have spoken about the single crystalline silicon. So, amorphous silicon is basically made by a chemical vapor deposition process, CVD process. Essentially that means that you create a vapor which carries these silicon atoms. So, typically from silane gas is used that has silicon atoms in it, and then you will have some substrate on which it can deposit. The nice thing about amorphous silicon is that it can be deposited on any surface. So, you can put a semiconductor on any surface, any curved surface, you do not have to worry about the shape of the surface. So, potentially for example, let us say you are trying to make a solar cell powered car. Instead of buying flat rigid flat solar cells and then placing it on top of your car, you can almost deposit this amorphous silicon all over your car, and so your car can be in any shape, you will have amorphous silicon all over it, and then you can use that for any process that you want. So, that is the basic idea, that in any shape you can do it. I mean that is the idea. It may not be that easy to just put it on the car, but that is the concept, that you can put it in any shape that you wish, and it also happens to be one of the cheapest ways in which you can handle the silicon. So, the issue with it is that it has dangling bonds. By nature an amorphous material is one where you do not have order, and therefore the bonds have not been satisfied. So, there are all of these dangling bonds which are defects from a crystallographic perspective, from a bonding perspective, those are considered as defects. The issue with the defects is that it impacts the movement of electrons or holes, and therefore if you are trying to use it as a semiconductor where movement of those electrons and holes is so important, this is a material that will actually get in the way of the movement of those electrons and holes, and therefore that is not particularly great to have. Then they have figured out that if you do hydrogenated amorphous silicon, which is given by this notation ASiH, if you do that by deposition from silane gas, then that hydrogen seems to do a good job of controlling these dangling bonds, and then that is a much better material to use as amorphous silicon, and then you can utilize it with much better capabilities. Okay. So, that is the basic idea. You take this vapor and then it condenses. When it condenses, it forms this amorphous material, and that material can be used, and that is how you get amorphous silicon. So, commercially when you look at least with respect to solar cell applications, those are the three types of variations of the silicon that is available: single crystalline silicon, polycrystalline silicon, and amorphous silicon. And we have sort of seen all of them. The original cleaning process that gets you that electronic grade or semiconductor grade silicon will typically get you, I mean most likely will get you all these polycrystalline samples. Then you do the processing, get yourself a single crystal, or you start with that material and given that it already has the purity, you do this other processing which gets you amorphous silicon. So, these are the two things that are done. So, we will close with this final discussion on the p-n junction. Having got your silicon sample, how do you get the p-n junction? So, normally what we do is we start off with a sample that is already doped in a certain way. It could either be the p type or the n type doping, and on that we introduce the other dopant. So, that is the typical way in which we do it. We introduce the other dopant into this sample. So, in this case for example, we can introduce it using ion implantation. This is generally a low temperature process. So, that is what is typically used. The idea here is that ionized dopants are accelerated using electric fields and implanted into that sample. This is considered a very effective way of doing this. The only issue with this is that it does some crystallographic damage to the sample, and so then after you have done this process, you have to do some annealing to sort of even out those the damage that you have done at a crystallographic level, smoothen it out and get it back to a fully functional single crystalline material. But it is a very popular way in which this can be done. The other way we could do it is to actually do diffusion, where you do a vapor phase deposition of some dopant that you want on top of the single crystal that you have, and then you have to do some annealing. So, this is now a high temperature process. You have to go to a significantly high temperature, maybe even say let us say about 1000 Kelvin for example. So, some high temperature you would have to go to, and at that temperature the dopants will diffuse. So, because for diffusion you need high temperature, and at that temperature only the dopants will diffuse. So, it needs thermal treatment which typically needs a significant amount of energy, but that is another way in which you can do this process. Here you are not really doing any damage to the sample, but inherently you have to do this diffusion because it will start from the top surface and move inwards. Finally, we can also do this thing called epitaxy. This is something that is done under very high vacuum, and what we do there is you take gaseous elements and they come and condense on top of the sample, and when they do so, because they are coming in almost atom by atom, they are arriving at the sample, they get an opportunity to line up perfectly in a crystallographic oriented manner on top of the sample that you have as your base material. So, that is another way in which you can get a junction. So, in all these cases you can get a junction where you have a p material as your base material, and on top of which you have grown an n material of some sort, either you have implanted an n material, or you have diffused in the dopants for an n material, or you have grown an n material on top of it. And so, that those are essentially the three ways in which we can create a p-n junction, starting off with any of the materials that we just discussed. So, in summary, our conclusions are these. It is quite challenging to produce a single crystal of silicon, but there are techniques that are there. Czochralski process is one, the float zone process is the other, and these are commercially being used in the silicon industry, semiconductor industry, but there is a lot of detail that is there, primarily because you want a well oriented single crystal and you want very high purity. Those are the two major challenges that are there. There are multiple steps involved, and as I said, purity and dimensions both have a very significant impact on the cost. If you did not have dimension as a requirement, if you did not have purity as a requirement, it is quite cheap. The minute you start talking of ppm and ppb and you want a single crystal that is say 300 millimeters in diameter or more, you want 400 millimeters diameter, and you start pushing that boundary, then the costs start going up. And of course, as I said, the other option that is available to us is amorphous silicon, which then is a much lower cost material, and it can be put in any shape, and therefore is a very convenient material to work with, except that performance wise amorphous silicon is essentially the lowest performing of the lot that we have discussed. Okay. So, those are the main conclusions for our class, and what we will look as we go forward is that having gotten some scientific knowledge on what the semiconductor is, how the band gaps are, and what happens with respect to the band gaps, what the p-n junction is, and now having understood physically how these things come together, we will look in our classes ahead on how the solar cell comes together and how the solar cell functions, and what are some characteristics that we need to keep track of for the solar cell. Thank you.